There are thresholds that define the degree of decline in relation to the different levels of threat. And you'll also notice, those of you familiar with the species protocol, that the thresholds are the same as those used for species, except for the historical time frame, which has higher thresholds because the assessment's carried out over a longer period of time. So to assess this criterion, one needs a time series of at least two different maps or sightings or other measures of distribution. And this is one example of an image analysis carried out at 2 points in time, 40 years apart, and it shows that in fact this ecosystem, which is a wetland, has had a net increase, which is the red areas on the map here, of about 10%. So it's going to come in here at least concern under this assessment for this criterion. It goes without saying that the quality of the data that goes into these assessments really matters a great deal to the outcome. If the data quality is not good, then the assessment will be unreliable. The second criterion, criterion B, is about estimating the size of the distribution, and this is about ecosystems spreading risk across very large distributions, or perhaps being susceptible to a small number of threatening processes or events within a very small distribution. We have two different metrics for measuring distribution size, and these are also the same as widely used in species assessments for that assessment. There are also sub-criteria which require evidence of qualitative evidence of a continuing decline in the ecosystem distribution or its function. We take account of fragmented occurrences by excluding them from the count of the number of grids that are occupied. So in this example here, this ecosystem is enclosed, its distribution is enclosed within a polygon that is about 5,000 square kilometres large, and it also is, it occupies about 46 of these 10-kilometre grid cells, of which 12 are occupied with more than 1% of the cell area, excluding the small fragmented occurrences. So both of those estimates lead us to the inference that this ecosystem meets the thresholds for an endangered status. These measurements and the use of these metrics are sensitive to scale. There may be different outcomes for the assessment if very fine units are assessed as opposed to very coarse units, and also fine grids are used as opposed to coarse grids. So in this example, we have the same distribution measured at different scales represented by different grid cell sizes, and you can see that the estimates change as the grid cell size or the scale changes. And for that reason, the protocol requires a standard method of measurement, which is based on 10-kilometre square cells. On to criteria C and D, which both deal with declines in ecological function. C deals with degradation of the abiotic environment, and D deals with the disruption of biotic processes. As you can see, there are varied pathways of functional decline. We may have a very severe functional decline that starts in a very small and restricted area and becomes more widespread over time, or conversely we have perhaps a rather benign severity of decline that is widespread and becomes more severe over time. So the criteria are structured to accommodate these different pathways, and only when we have both an extensive and very severe functional decline in the ecosystem does it qualify to meet the highest category of risk, critical endangerment. And these assessments again are carried out over the 3 timescales that I mentioned earlier. One of the key issues in assessing functional decline in an ecosystem is choosing the variables for assessing the severity of decline. And the key requirement is that they must represent a key ecosystem driver or threatening process that affects the ecosystem function. So proximal variables are going to be better than indirect ones. Ecosystem-specific variables are going to be better than generic ones. Sensitive variables are going to be better than insensitive variables. And the choice needs to be informed by a cause-effect understanding of the processes that operate in the ecosystem. So to assist that process, we're suggesting that part of the assessment process is about developing simple graphical cause-effect process models that identify the major drivers of ecosystem change. And in the case of this wetland, it's all about the water balance and the hydrological cycle. So that leads us to infer that variables such as precipitation, evapotranspiration and groundwater levels might be useful variables for assessing functional decline in that ecosystem. Here's another example with a biological focus. The kelp forests that occur in the northwest Pacific, which are linked to the pelagic ecosystem where killer whales are hunters of seals and great whales and fish, all of which have been exploited by humans, resulting in declines in their populations, and coincidentally a dietary shift in whales which have moved to sea otters. The decline in sea otter populations has affected the sea urchins on which they are predators, and the sea urchins in turn are predators of the kelp. So the absence of otters from the system allows this switch to occur from kelp forest to urchin barrens. So in this case, the abundance of sea otters is perhaps a useful variable for assessing ecosystem decline in function for criterion D. So we have this series of steps for assessing declines in ecological function. The first is selecting a functional variable, which I've just taken you through. The second important step is to estimate the collapsed state in relation to that variable. So here's an example of a floodplain forest or woodland system where it's been observed that over time a certain level of stream flow results in extensive tree death because the survival of the trees depends on regular flooding. And from this period here, we're able to define this zone of potential collapse in the ecosystem, which, if river flows were maintained at that level for an extended period of time, then we may expect the ecosystem to collapse. So the second step is, or the next step rather, is about estimating the initial state of the system. And if we're talking about the present, we will go back 50 years and estimate river levels at that time, which in this case we've averaged over a 50-year period up until 50 years ago. That's 712 centimetres. And then we estimate the current state, which is the mean maximum river height for the last 50 years. And then we can calculate the decline in river height over that 50-year period, the observed decline, relative to the decline that it would take to collapse the ecosystem. So it's this blue quantity divided by the red quantity that gives an estimate of relative severity of that degradation of the ecosystem. And this enables us to compare it to the thresholds in the criteria and infer a vulnerable status for this ecosystem. The fifth criterion is about bringing all of these factors together, all of these different symptoms, if you like, into a model to come up with an estimate of the probability of collapse. Different kinds of models are possible to build and already exist, and they have varied data requirements. We have made some limited progress on this so far, with one pilot study completed, and we have a research agenda to progress the development of such models across a wide variety of different systems. That's all I have time to say to tell you about that particular criterion. So in terms of an overall assessment, we can consider the 5 criteria and apply them to an ecosystem where the data are available. And in this particular example, we see that this ecosystem has a projected future decline in distribution, which is related to declining rainfall with climate change, and also a declining habitat suitability because of the same mechanism. So the risk assessment, we take the 2 highest criteria that yield the most extreme levels of risk as the overall status, and the risk assessment implicates climate change as the greatest threat, and therefore a focus of future efforts should be adaptation strategies to deal with that change. Another example from the Caribbean reefs shows that the critical factor here is a decline in coral cover. And so that points us to a situation where we have to consider strategies for managing disease and adapting to climate change, which appear to be the underlying causes of that trend. So to conclude, we have completed so far 18 different case studies, which are very detailed. They span a full range of ecosystem types from around the world. Some of them are data-rich examples, some of them are relatively data-poor. It's interesting that even the data-poor ones, we have been able to find sufficient data to assess those ecosystems against at least two of the 5 criteria. And for the majority of examples, even more criteria, at least 3. The results also show that different criteria determine the overall status of the ecosystem. And that's encouraging because it means that these criteria really are representing different mechanisms and symptoms of decline, and their ensemble properties working together are providing a more comprehensive assessment of the overall risk. Thank you very much.
David? Good. Maybe we could do a quick little 5-minute, 4-minute round of questions, anything pressing, and then we move on to the case studies. Anything? Yes. Take the microphone, please.
My name.
Okay. You switch to
My name is Anthony Benjamin. I'm the Deputy Chair of the Commission on Environmental Law. I have to say that this is the most fascinating development in science that I see as having a potential to change environmental law and conservation law. And I am delighted that by accident I entered the room. I am aware of the project, and I'm just surprised that the Commission on Environmental Law has not brought itself, even without an invitation, to work together with this extraordinary project. Let me say a few things from a legal perspective about what you are doing, and perhaps you don't have a clear perspective of how a gigantic transformation this is in legal terms. One, because it changed completely the paradigm that we lawyers have been using for 100 years in dealing with endangered species, which is much more less difficult, I'll not say easier, but less difficult for us lawyers to work with, because it's one thing at a time. But the problem is that we never, and I'm a judge in the Supreme Court of Brazil, we never have the broader picture. And because species are spread out in the territory of the country, it means that cases that, and some of them are endemic to particular biomes, it means that judges tend not to have a clear picture of what's going on all over the country, because they concentrate on a specific species and so on. So this is absolutely fantastic from that substantive law perspective. But there are more implications in what we're doing. It has to do with what, without having the scientific background, we have been proposing the establishment of the so-called ecosystem judges in different countries. So judges that instead of having a territory assigned, jurisdiction assigned based on traditional terms, those judges will have an ecosystem, of course not a biome, and I'm not taking the very broad concept that you explained there, of an ecosystem, but a more manageable a concept of ecosystem. And this judge then would be much more, it's much more easy for, if we have the scientific basis here, to propose it. And finally, but I mean, I will have so much to say, but I'm sure we are going to have other opportunities in the next, 20 years. I hope I'm alive. 40 years, because this is developing. This is the first time this scientific concept evolves in conservation that law can be part of at the very beginning and not at the opposite side. Which means that we can avoid the mistakes on the scientific level that make it impossible for lawyers and for judges to implement those concepts. Take, for example, the concept of ecosystem. There are many laws that define ecosystems, and there is no coherence, and the scientific basis for that is very weak. The different categories of threatened species. And I said it was my last point, but there is even another one, and then I'll stop. But I'll say, which is we in this area can we should not wait until the scientists, you are the scientists, reach conclusions. Because we lawyers, what we need is what we already have. The detail, if you go to legislation and even to constitution about endangered species, the details are not there. It's the broader picture. So this means that we in the Commission on Environmental Law should be part of this. And I do hope that in the next 4 years we work together and perhaps we have a joint special committee doing this. But working at the legislative level as we speak. I would have one question, since I suppose I can ask a question. What do you do with ecotons? When you have 3, 4 different biomes or ecosystems, broadly defined ecosystem, how are we going to assess risk and risk of extinction? Thank you.
Thank you.
A very short answer.
Then we move on to the presentation.
A very short answer. I think the best way of dealing with ecotones is to carry out assessments at multiple levels of classification, because ecotones and broad levels of classification between two very broad ecosystems can be classified as an ecosystem themselves at a finer level of organisation. So we need multiple levels of assessment.
Bonjour, je vais vous présenter le travail qui a été réalisé dans le cadre d'un stage master fait cet été par Aurélien Carré, qui était co-encadré par moi-même, Brigitte Poulain et par Marion Péguin du comité français de l'IUCN. Donc l'écosystème concerné est les lagunes qu'on retrouve en France. Donc l'échelle spatiale, c'est bien la France métropolitaine. Cependant, ces lagunes ne se retrouvent que sur la côte méditerranéenne. Si on décrit brièvement l'écosystème, donc ça consiste en des masses d'eau saumâtres, peu profondes, qui sont séparées de la mer par un cordon dunaire qui peut avoir un ou plusieurs gros brèches qui sont permanentes ou temporaires, qui permettent les échanges entre le bassin versant et la mer. Ce sont des milieux productifs, riches en nutriments, qui sont généralement entourés de zones humides comme des mares, marais, sansouirs, qui sont aussi intégrés ici dans le cadre de l'évaluation. Je n'ai pas vraiment eu le temps de présenter les espèces clés de l'écosystème, mais bon, c'est des milieux qui sont généralement riches en herbier, qui sont des sites importants pour l'abinage des poissons, qui sont aussi beaucoup utilisés par les oiseaux, par exemple. On a considéré ici que les lagunes sur le littoral méditerranéen, de par leur fonctionnement très différent et leurs caractéristiques aussi biotiques, pouvaient être considérées comme un écosystème différent des marais, par exemple, littoraux qu'on retrouve sur la façade atlantique ou encore sur le long de la mer du Nord. L'évaluation a été réalisée sur 27 complexes lagunaires et leurs zones humides adjacentes qui ont été regroupées en 12 unités majeures, chacune évaluée de façon individuelle. Pour le critère A, qui consiste en la réduction de la distribution géographique, on a considéré que le principal facteur impliqué était le comblement, qu'il soit de nature naturelle ou anthropique. Pour le facteur A1, qui concerne les dernières 50 années, le statut est least concern, non concerné. En fait, on a observé des régressions significatives dans soit la superficie ou le volume de certaines lagunes, mais seulement des lagunes de petite superficie qui représentent à peine 5% de l'écosystème global. Pour le critère A2, donc les 50 prochaines années, on obtient la même catégorie, donc non